Hello?
Yeah, we can hear you. Yes.
Okay, great. Yeah, I had some difficulty with the computer just like a few minutes ago, but thankfully it's all okay. You can see me as well, right? Is the voice okay? Do I have to shout a little bit?
No, it's fine.
Yeah, it's fine, sir. So I think we can start.
It's 1:55, right?
Yes.
You can introduce chairman and then chairperson and then.
Okay, yes, sir.
Should I share my screen? Is that not necessary?
No, I will.
Might not
I will let you know that time. Okay.
Okay.
So
Perfect.
yeah. Okay. Welcome back to the second international conference on sculptured thin films, GLAD 2021. So now we are going to start our second session of the day. So for this session we have the chairperson, Professor Mukesh Kumar, with us. So Professor Mukesh Kumar is the Associate Professor of Physics Department at Indian Institute of Technology, Ropar, Punjab, India. Dr. Kumar has received many prestigious awards like Young Scientist Research Awards from Department of Atomic Energy, Bhaskar Advanced Solar Energy Fellowship from Indo-US Science and Technology Forum, Young Achiever Award from Bhava Atomic Research Center, Faculty Research and Innovation Award from IIT Ropar, and Fulbright Nehru Academic and Professional Excellence Fellowship from US India Education Foundation. Professor Kumar is also a member of Indian National Young Academy of Science and the National Academy of Sciences, India. His research is focused on functional and renewable energy sources for photovoltaic, broadband photodetectors, and hazardous gas sensors. So I would like to request Professor Mukesh Kumar to chair this session. So over to you, Professor Mukesh.
Thank you very much, Shank. And it's wonderful going. Like I attended all the talks, and it is really informative. So maybe it's time to introduce the speaker. So in this last session of this international conference on GLAD, we have total 3 invited speakers and 3 oral presentation. So we have first speaker, Professor Amrish Ghosh from IIC Bangalore. So Professor Ghosh is graduated with a 5-year integrated MSc in physics from IIT Kharagpur, and he completed his PhD from Brown University, where he was working on electron bubbles in superfluid helium. From 2005 to 2009, he was a postdoctor at Harvard University, working on optical and hydrodynamic properties of chiral media. In 2009, he joined IIC Bangalore as a faculty, and his research interest includes the study of quantum fluids, plasmonics, driven colloidal systems, and their applications in biology. And he received many national and international awards. So, Professor Ghosh, over to you. And his title of the talk is Multifunctionality to GLAD, Challenges and Opportunities.
Great.
So I'll request you to just end up maybe 25 minutes so that we can have time for question and answers. Thank you.
Yes. Thank you. Please let me know 5 minutes before, Mukesh. Thank you. Thank you for the kind introduction. I hope you can see my screen. Not yet, right?
Not yet.
Okay. Okay.
Yeah, it is coming. Yes, it is.
Okay, great. All right. So thank you, the organizers, Professor J.P. Singh and Waiping Zhao, for inviting me to give this talk. I'll go a little quickly. So as you see, the title of the talk is Multifunctionality Using GLAD. I'm going to give you a bunch of test cases where the issues are and what the successes are. Most of this, well, all this work is carried out at the Indian Institute of Science, Bangalore, at both the departments of physics as well as Center for Nanoscience and Engineering. So before I start, let me thank the past and present group members who have contributed to this work in a very major way, without whom this work would not be possible. And also the long list of collaborators from various different disciplines with whom we had the good fortune of collaborating. So, and of course, funding is extremely important. Let me go to the crux of the matter. I don't have to explain in this audience how GLAD works, but rather the theme of my talk is how you can use GLAD and other techniques to have multiple functions integrated in one system. So this can be obtained through use of multiple materials. For example, in the same system, you can have magnetic property, plasmonic property integrated. And apart from materials, you can also try to integrate different type of fabrication techniques. So along with GLAD to create such nanostructured thin films, perhaps you can also combine PECVD, microwave synthesis, and a couple of other techniques to have new functions, not only across a wafer, but also colloidal suspensions that you can get out of that wafer, right? I will going to point out how geometry plays a very major role in, for example, the case of helical nanobots, which I will tell you the width of the helical filament makes a big difference, which I'll give you some examples of. And then also how you can use the other techniques to have different configurations. So for example, what happens when you create some form of a coarse shell type of a geometry. And this is the sort of overarching theme of what I'm going to talk here today. So I've already told you a little bit about the experimental system. The key idea is the talk is sort of broken into approximately equal parts. On one hand, I'm going to talk a little bit about the different types of nanophotonic devices, and these are really devices made of films, where we have given different types of interesting photonic or optical properties. And then I'm also going to tell you about helical nanobots, which are effectively colloidal suspensions that one can derive out of these nanostructured films to get new functions. Okay, so that's the structure. Plasmonics has already been mentioned many times in this talk. The key idea is these are localized excitations of the free electron plasma inside metals or metal-like elements. They can be excited by direct light illumination, and there is a very strong dependence of shape, size, and surrounding of LSPR, or localized surface plasmon resonance. The key question that we have addressed in our research program is the effect of coupling in localized surface plasmon resonance. Now, we know that if you have two plasmonic particles, and if they are really close together, then the local electric field is governed by the near field effect of the dipole, which goes as 1 over distance cube. So if you have two particles, the 1 over distance cube term of the electric field will dominate. And as a result, you can create these extremely large local electromagnetic hotspots at the junction of the particles. Now, this coupling is strongly polarization and distance dependent. So for example, when the polarization direction is parallel to the interparticle axis, you start seeing a strong field enhancement, and you are going to have some sort of a redshift as you keep on increasing the coupling by bringing the particles close together. Alternately, you can think about the polarization being perpendicular to the interparticle axis, and in that case, well, there is only slight blue shift, the electric field enhancement is probably not so large, so on and so forth. So the point is the geometry can play a very important role in plasmonic coupling. Now, this is the near field for the sake of completeness. Let me also clarify that there can be also far field effects, which goes as 1 over the distance or 1 over the separation. And there you can start seeing diffraction-like features. not so important from the perspective of this talk. I will get to the near field part again in just a little bit. Now, the key question that we addressed, and this was almost about 9 years ago, is that, well, people have looked at localized surface plasmons, and coupling of localized plasmons is of great interest. Now, can we extend this to 3 dimensions by placing this sort of plasmonic particles in arbitrary geometries in 3 dimensions? And of course, one of the answers to that was, well, in 3-dimensional fabrication, can we try glancing angle deposition? Again, this is something that this group knows very well. Well, it's not completely trivial to do GLAD with metals because metals have a low melting point. So the surface diffusion of the metal atoms is going to destroy the shadowing. So of course, one of the ways, and this is what is shown here with a melting point 1700 Kelvin, you have this nice structure, while something of this low melting point, well, there is not much of a uniform structure. So one of the ways of countering this would be to cool the substrate, and I think Pierre's group have done phenomenal work in this topic. Another very simple way of dealing with this is to do seeding. So for example, we can have some form of a nanostructured surface. So whatever metal comes in sort of remains in one place. And I'll tell you how this can be useful. Now, for the sake of completeness, I must add that another way of doing this is to have some form of a co-evaporation. And in this case, Wiping's work using titanium and silver together has been quite phenomenal. So with respect to the nanostructuring, and this was our approach, one of the things we wanted to do, and almost 8-9 years ago, was to create this type of geometries in which we have some metal dielectric alternate layers. So the SEM image, you can see these black stripes. These are actually little silver discs that are separated by a little bit of dielectric, which in this case was silica. Now, one of the advantages of something like this is it's a very nice and powerful substrate. It's completely wafer scale. You can have a very large number of electromagnetic hotspots, and you also have a large surface area and therefore a lot of loading of particles. And indeed, as we increase the number of layers, we found the signal to really go up dramatically. So this is one of the work that was published almost 9 years ago. Now, while we were doing this work, it's sort of a question that sort of arose, is that, well, what happens when, at this metal dielectric metal layer? So of course, we know that as you bring this metal plasmonic particles close together, and if you shine light, there is going to be a tremendous field enhancement at the junction of the particles. And these are just calculations that shows that, okay, when you shine light along the interparticle, well, in this particular case along the axis, you'll start seeing a large field enhancement at the junction. And simulations show that as you change the gap from, let's say, 34 to 0.34 nanometers, the local electric field can go up by, well, at least 3 to 4 orders of magnitude. So, of course, it makes sense that if you really want to have very strong hotspots, you would like to make this dielectric thickness as low as possible. So the question that we wanted to ask is how small this d should be. And the answer is actually a little non-trivial. Smaller is not necessarily better in this particular case, because as you keep the particles bring closer and closer together, at some point quantum tunneling is going to take over, and subsequently the entire enhancement of the electric field will be lost. And typically the range, the length scale at which the bringing them closer does not work anymore turns out to be about 3 to 5 angstroms. So really an ideal configuration of this type of a nice 3-dimensional hotspot geometry would be to have these layers of plasmonic particles that are separated by a material of, let's say, thickness 3 to 5 angstroms, and as it so happened, the layer of thickness of a single layer of graphene is 3.4 angstroms. So it's right in that range. So this was the work that was done by Devadrita, a really fantastic piece of work in which she first made this monolayer of silica beads, which is just a way of creating an overall structure that's about half a wavelength or about a wavelength away. And then once you do this, we deposited a layer of silver. Yeah, deposited a layer of silver, which basically, and in this particular case, we did cool it down to about, actually not 80, more like 140 Kelvin or so. But then once these structures are formed, we annealed them. And once the silver was annealed, it created these tiny little spheres on the top of each of these colloidal particles. And the separation is of the order of 500 nanometers. Subsequently, we transferred a layer of CVD graphene. And this is what you are seeing here. The CVD graphene layer is being transferred. You can see some cracks in the graphene layer. And the key step is the second glancing angle deposition, which allows the silver to fall right at the top of these hills. And then an annealing step gets formed such as to make a layer like this. So the net result, and I really like this picture, is what you're seeing here. Maybe you can concentrate on this part. What you see is a silver sphere below the graphene. That's why it's slightly translucent. And then a silver ball right above. So what you are seeing are two silver particles around 140 nanometers or so that are separated by exactly 3.4 angstroms, not even half an angstrom more or half an angstrom less. Now, it's interesting, of course. Now we wanted to look at their optical property, and one of the ways of looking at their optical property is to look at the Raman spectrum of graphene. So as one would expect, the Raman signal from the graphene pretty much went through the roof, and it all made quantitative sense. And when you did some form of a map, the Raman map, we found out the enhancement to be typically coming from the junctions. Basically, right at the junction of the two silver particles, the signal of graphene really went up. Okay, so some form of an hexagonal lattice was observed. Now, what is the benefit of doing something like this? So we made a photodetector device out of it. And this is a completely wafer scale technology, remember, CVD transfer, CVD graphene, glancing angle deposition, these are all wafer scale technologies. So we had a source and a drain, and this is our graphene device, which is sandwiched between this silver dimers. And then we looked at the source and drain current as a function of wavelength and power. And what we found out was a large amount of photocurrent induced in this channel when you turn the light on versus off. And the peak amplitude, the peak photoresponsivity went up to few amperes per watt, which is actually significantly larger than all previous plasmonic graphene devices. So there's a lot of detail about it. And one of the things I would love to answer at the end of this talk is exactly why there is a field enhancement. Because if you think about it, your light polarization is actually perpendicular to the interparticle axis. And by something that I said before, you should not be having any field enhancement at the junction. But I can answer this question a little bit later if you're interested to know. The key point is you can have these extremely large enhancements, and there is going to be some new work coming from our group very soon with respect to better understanding of the plasmonic phenomena, as well as using not graphene, but some other two-dimensional layers. Some work is going on in this direction. A little bit change of theme, and I'm now going to talk about chiroplasmonic substrates. A lot of people have spoken about this, using this type of plasmonic helices and stuff like that. And it's a very nice and vibrant area of research and a great application of GLAD. We had a slightly different strategy here, in which what we did was to take these dielectric helical templates, and then decorated them with silver or gold nanoparticles. And this is what is shown schematically here. When you shine light onto this object, each of these little plasmonic particles are going to have some dipole moments induced. These dipole moments are going to interact with each other, predominantly through Coulombic interaction. And then when you shine light, you have to realize that these plasmonic interactions are in a chiral geometry. So therefore, the net optical response of the system will depend on the chirality of the light, or in other words, they will differentiate between left and right circularly polarized states of incident light. So schematically, we first make the helices shown here, and then subsequently we turn the substrate a little bit, and then do basically put them with a large number of plasmonic nanodots. The result, again, these are all wafer scale devices. And the differential absorption between left and right CP light scaled by the average absorption is actually about 30–40% or so. It can go up to, in our latest results, we had about 78% or so, which is of course orders of magnitude compared to most natural occurring chiral materials. And one of the attractions about this is that it's an extremely simple thing without requiring any cooling whatsoever. We of course do not need to get confined to plasmonic devices, but we can also think about dielectrics. And this is something that Johnson looked in great detail. And here is one example of GLAD combining with PECVD, a different fabrication technique. What he did was to make silicon dioxide helices and then used PECVD to have a layer of silicon all around it. And silicon being a strong, a very high refractive index, works like a little nano resonator, but this nano resonator is chiral in nature. I do not have the time to go into this detail, but the key benefit of doing this particular type of a device strategy is that there is no plasmonic loss. It's predominantly a scattering-based phenomenon, and the differential transmission is extremely large. And what's a little bit more interesting as well is the resonances that happen here are actually magnetic dipole in nature. More details are there in this 2018 paper. I also wanted to, and the SES photonics paper, I also wanted to let you know that many of these effects are also perfectly realizable in nonlinear optics. Okay, so with this, I would like to have a little bit of a change of gear and want to go into a different system. And this again, of course, comes from the GLAD fabrication technique. But now we don't talk about optical properties of films anymore, but rather talk about colloidal suspensions that you can get out of these nanostructured films. So the motivation of this magnetically driven helical nanobots, let me first clarify, just having a magnet close to a suspension of magnetic particles should not be called a nanobot, or at least we don't call it in that manner. This sort of gradient pulls are not very strong when things get smaller. So it is better to, or a preferable way of moving small things would be to use some form of a corkscrew motion like bacteria, as is shown in this movie. And there are very interesting papers that people have written on this. Okay, so what we have done using GLAD is to make this small artificial corkscrews and then using that to move them in fluids. And that's our basic name of the game. Typically, these nanohelices were formed making some form of a colloidal layer and then making the helix on top of it. And then you can attach some magnetic material or attach fluorescent molecules to it. Schematically, what you have is a helix with a permanent magnetic moment that is attached to the helical structure. Of course, you are not limited by these huge structures, but you can make things much, much smaller as well using different types of pre-seeding techniques. So the seeding will play a primary role in making the size of the helix smaller. But I believe most of you know this one. The way the motion is obtained is by using this helix with a permanent magnetic moment shown in red. When a magnetic field shown in blue is rotated, the screw rotates in sync with the field, and as a result, you can move things forward. You can move things with really, really good control, and you can move not just one, but millions of them all in one go. Okay, you need not be only dealing with ferromagnetic structures, but you can also do superparamagnetic structures and stuff like that. So some more work on this is in process. There are many different ways in which you can introduce the magnetic materials. So here, for example, we put the magnetic material while we are growing the helix. Here we have already grown the helix and we have attached some magnetic material on top of it. Here we have grown the magnetic elements on 3 different lengths of the helix. And using this way, you can have a very nice way of controlling their magnetic property. See, there are ways in which you want to make the magnetic property large, but there might also be situations where you want the magnetic property to be exactly in some range with some control over the hysteresis curve. And to have, there are, I can tell you many different possibilities that will emerge if you have really good control over the magnetic properties. A little bit of this was mentioned by Pierre when he was talking about the iron platinum thing. And then similarly, one can have many different functions that can come from this magnetic properties. Here again with these helical bonds, by the way, you can also have covalent linkages to attach it to different chemicals. Okay, so many materials configurations are leading to functionalities. A very important aspect is to know the thickness. Okay, so again, using something like block copolymer micellar lithography, one can make things very, very thin. There are many other ways of reducing thickness as well. Now, reducing the seed size and therefore a lower thickness of the helix turns out to be a crucial parameter if you want to move things in biological environments, because most of the biological environments are naturally porous in nature. So ideally, you want the helix size to be comparable or smaller than the size of the pores. And this is something that we luckily found out when we were doing this experiment of motion of the swimmers with living cells. So this was a really fun experiment in which we took these cells and incubated them with the helical swimmers. And then we incubated them for about 24 hours. And then what we found out is that the helices were internalized by the cells. So what you're seeing in this stack of confocal images, if you look at the movie a little bit carefully, the green is the cytoskeleton, the blue is the nucleus, and the red is the helix. So depending on which layer you are, you would be able to see that there are total 2 helices that were internalized by the cells. Now, getting internalized is not very surprising. What was very surprising was that the helices were actually able to move within the cell. So what you are seeing here is actually the motion of the cell, of the swimmer inside the cell. And here is a picture in which the swimmers were getting manipulated. And during that time, the cell decided to divide. So this is, we are really very excited about this new direction, because you see, this is a great new tool for intracellular biophysics, because what we have been able to see is that these objects can move inside the cells with a lot of control. It's not like just letting it go and it will go straight, because the cytoskeleton is a very constrained surrounding. Only helices thinner than 250 nanometers would work, at least in the cells that we have looked at. And as you move forward, quite often you go and bump into something, then you take a step back, change your direction, so on and so forth. And Malay and Somal were really become experts in this. And well, they even decided to write M and N within the cell. We believe that this will be a very strong tool for mechanobiology, because by looking at the speed, we would be able to understand and measure the local viscoelasticity as well as flows that are happening inside these living cells. So this is something that I think is going to be very, very interesting. I will just say a little bit about the core shell strategy. This was Lakshmi's work a long time back. So what she found out, she wanted to move this helices inside blood. And what we found out was, well, the blood is an extremely corrosive material. So after some high degree of trial and error, she combined microwave synthesis to GLAD and then added this layer of zinc ferrite. What this does is it gives 3 functions through one shell, which is that of ferrite. Firstly, it protects you against the chemical corrosion. Secondly, by putting a spacer layer, it actually allows the helices to not clump magnetically against each other. And then finally, the ferrite shell is known to give heat when you put it in an alternating magnetic field. So this can also be used for magnetic hypothermia. So this, I think, is a very ideal example in which one extra step can give you 3 functions all in one go. I'm trying towards, I'll just say one last thing, and after that, I'm going to end my talk. And here is an example of plasmonic integration on the helices. And in this particular case, we have integrated simple nanoparticles on the helix body. And when we shine light, we have 2 properties integrated. The magnetic swimmer property integrated with the large local field that happens around the plasmonic particles. When you are in a fluid, these plasmonic particles will act as little optical tweezers. So if you have any colloid nearby, they will get attracted towards these plasmonic islands. So what we would do, we will take this swimmer, bring to a colloid of interest, turn the light on, trap the colloid, move the colloid from point A to point B, and in this point, by turning the light off, we are going to release the cargo. And this is the movie that you will see here. The swimmer goes towards the cargo of interest, turn on the light, two colloids get trapped, and then you go from point A to point B, you're transporting the colloids. At this point, you're going to reduce the light intensity to release the smaller colloid, and then you turn the light off to release the bigger colloid. Okay? So this is a case of a trap, transport, release of cargo. You can do this very easily for sub-100 nanometer particles using light intensities that are far lower compared to what you would need for standard optical tweezers. Here, the integration strategy makes a humongous difference. You can either have a large number of plasmonic particles integrated throughout the body of the helix, or you can have the plasmonic elements only at the neck of the helix. In both the cases, you have a strong local electromagnetic field. However, the left one with a larger number of smaller particles will give a lot of heat, and therefore a lot of thermofluidic effects like convection and thermophoresis. The one to the right, where all the plasmonic particles are just here, will give same electric field enhancement, but much lower heat and therefore no thermoplasmonic effects. And depending on what you want to trap, you can use either of the geometries. And this was shown in Rohit's papers in great detail. I would not talk about the last part, which is related with how you can control the surface charge for cancer imaging. But this is a very recent and exciting work that was done by Devan and Dharma. I will not get into the detail, but rather let me conclude by saying a few things. By playing with this configuration of materials and geometries, you can have multiple functions within a single film or a single nanobot. And currently we are looking into, of course, our dream of fantastic Voyager is very much alive. And we want to, this is going to be our top priority, along with trying to make new active photonic devices and quantum sensing applications. We believe that our system is very, very well suited for studying the physics of active matter because you can engineer asymmetries as well as interbot interactions. And then we think that the field is right now in a state that's matured enough that we can actually try practical medical applications. And we have a recent spin-off from our group in the field of dentistry, which is looking at this quite seriously. With that, I would like to thank you for your attention. And as you can see, this is a pre-COVID picture. And I hope all of you are keeping safe and secure in this very difficult times. Thank you so much for your attention.
Thank you very much, Professor Ghosh, for, as usual, very excited talk. Now, I invite the questions. Yeah, Shashank.
Thank you, Professor Ghosh, for this excellent, wonderful work which you are going on. So I have one question that you are using the graphene in between the silver and silver monolayers. So what do you think about the spectra of graphene itself? Because graphene has a good Raman spectra, so it can suppress the analyte Raman spectra. So how do you comment on that?
Right. So we are not looking at source of an analyte when we looked at the source signal. We looked at the source of graphene itself, which is exactly what you are saying. So the Raman spectra that we showed there was that of graphene. The Raman map that we showed was that of graphene itself.
So can we not use it for other purpose, other molecule detection?
So I think the answer is possibly yes. But maybe I'll just take you to that diagram. Okay. So I suppose the point would be So I think the question is whether the molecule will be able to reach the place of the maximum field enhancement. And this is not a trivial question to answer because, I mean, at least from an experimentalist perspective, the graphene is going to be, I mean, it's not going to be a point contact between the sphere and the graphene. There is going to be some form of, I think there might be some form of a facet formation, and this is going to change the space that is available for the molecule. We do not have a clear answer for that, but I think these are the sort of details that one would have to consider if you want to use this device for source of analytes.
Okay. And my another question is like how the search signal depends on the chirality of the molecule. So do you think it is going to be different for the left-handed or right-handed molecules?
Okay, so we never did this. We never looked at, we never did search with the helical structures. But what you are saying is highly valid because we have actually calculated this. Indeed, the local field around these helical structures have a strong so-called chirality parameter. So they are basically strongly twisted. I think people in the literature call them, what is it, super chirality or something like that. I mean, effectively, this chirality parameter is very large, which in turn can result in a stronger enantioselectivity between the, or enantio differentiation between left-hand CP, right CP light. But we have not done it with our chiroplasmonic substrates. We only looked at the absorption or scattering difference of these substrates.
So by principle, it is possible, you want to say?
Yes.
We can do it.
Yes. Yeah, I mean, the numbers seem to be that it has a very strong chirality. It has a very large chirality parameter around the plasmonic particles.
Okay, thank you. Thank you so much.
Okay, so we can take one more question for Professor Pierre Fischer.
Very nice. Thank you, Ambrish. I would like to ask, have you estimated the force that these rheology probes can achieve? Because in the cell, this is probably a difficult environment. So I was wondering if you have a number, and that also would compare then with tweezers, right? How does it fit in both your effects grabbing things as well as moving? And what force range do you think is achievable?
Right. So that's a great question. For the tweezers, I believe the record numbers that I've seen are with 400 nanometer beads, and they turned out to be of the order of 50 piconewtons, if I'm not mistaken, right? I think that's the right number. 50 piconewtons with 400 nanometer beads. I think it is possible to achieve this, but I feel rather than trying to go by the force way, it might be better to try to do it the shear way. So rather than trying to see how much translational force or pressure you can generate, it might be better to ask the question how much torque you can, or how much local shear you can generate with the helices. And there, I don't have the offhand number with me. I think you can go really much, much better compared to most magnetic tweezer effects.
Thanks.
Thank you very much, Professor Ghosh, for a very nice talk. Thank you very much. So we will have now the oral presentation. So the first presentation by Dr. Samir Kumar from Kyoto University, Japan, and he will talk about the water droplet bouncing on a non-superhydrophobic silicon nanospring arrays. Dr. Samir.
Thank you. Okay. Yeah. Share.
So I will appreciate if you can wind up in 12 minutes so that we can have 3 minutes for question answer.
Okay, I'll try. So, hello everyone. I'm going to talk about the water droplet bouncing on a non-super hydrophobic silicon nanospring arrays. And so I'll start with just a brief overview of the wetting, then our results and the possible reason for the bouncing mechanism, and finally the conclusion. So how to classify a surface contact angle? It is the angle that the water droplet or any liquid makes with the surface. So it can quantify the type of surface, whether it's hydrophilic, hydrophobic, or super hydrophobic, depending upon the contact angle, which can be less than 90 degree for hydrophilic surfaces and more than 90 degree for hydrophobic surfaces, and for extreme cases more than 150 degree, the surface can be super hydrophobic. So there's various methods, chemical and physical, to make these surfaces super hydrophobic by chemically coating by surface and monolayers of low surface energy chemicals, or by creating nano roughness on the physically on the structure. And previously, GLAD has been used to modify these wetting behavior of these nanostructures, either by changing the different parameters, like changing the density of the nanostructures by varying the deposition rate, or by changing the diameter of these nanorods by reducing the deposition temperature. So in this work, I'm going to talk on the water droplet bouncing on silicon nanospring arrays. And for this purpose, I'm mainly concerned on the dynamic behavior of these water droplet on these nanostructures. And we fabricated 4 types of nanostructures, basically 4 samples, of which 3 were nanostructure samples, and vertically nanorods, slanted nanorods, and silicon nanosprings, and one was plain thin film. And these nanostructures were around 250 nanometers in thickness and with average diameter of around 50 nanometer. However, the apparent contact angle on these nanostructures were more than 130 degree, around 136 for slanted and nanospring arrays. But for vertical columns, it was almost close to 150 degrees. And this increase in the apparent contact angle can be explained on the basis of the Cassie-Baxter model, so which sees the surface, explains the water droplet sitting on this surface as a composite surface of air and the silicon. And by reducing the solid fraction of this surface, by creating the nano roughness, the contact angle can increase. So we calculated the solid fraction of these nanostructure surfaces, and we found that the vertical columns has the lowest solid fraction of about 20%, and hence has the highest contact angle. And it matches well with other results also. I'm not shown here. So next, our first observation was the dynamic behavior of the water droplet on these nanostructures. So for that, we dropped 10 microliter of water droplet from different height, from 10 mm to 20 mm height, and we study how these droplets behave. And sorry, it's not playing, but these are the snapshots of the same video, and you can see that the water droplet left the surface for only for vertical columns and nanospring surface, but for the slanted column, it does not left the surface, or no bouncing was observed. And the second observation was that the rebound time for the water droplet was almost constant for the vertical columns. However, for the nanospring, it was found to slightly increase from 15 to like 18 milliseconds. And also the loss, the coefficient of restitution, which is a measure of the energy loss between when the two between the collision between the two objects. So the coefficient of restitution for the water droplet was on the vertical column was almost constant. However, for the on the nano spring structure, it was found to slightly increase. So and so how to explain these observations? So there we tried 4 possible regions, and so the bouncing behavior can be because of the superhydrophobic nature of the surface, because there is very less interaction between the surface, or when the work done by the liquid to overcome the resistance force produced by the contact angle hysteresis is very low, then it can also bounce, or when the capillary forces produced by the nanopillar surfaces is very high. Or the fourth one is our hypothesis that the nanospring has an elastic property that plays a significant role on the bouncing behavior of the water droplet. Next, we'll see whether these are the possible explanation, or whether these 4 points are able to explain the bouncing behavior of the on the nanospring structure or not. So first we'll see, we can clearly see that this cannot be the reason for the bouncing behavior on the silicon nanospring array, because the contact angle was very much less than 150 degree. However, for the vertical columns, this can be the reason, because it was very close to contact angle around 150, and with plus minus of 4 degree, it's almost more than 150 degree. So this is not the reason for the bouncing behavior on the nanospring arrays. So next, the work done on spreading and receding the water droplet on the surface is given by this equation. So where theta r and theta a is the receding and the advancing angles. So receding and advancing angles, which is taken when we are dropping. Receding angle we calculated when we are pulling up the drop, and advancing when we are dropping the droplet. So we found that for vertical column, this contact angle hysteresis was found to be very low. However, for the nanospring arrays, it was higher even than the slanted columns. So, but we observed the bouncing so on this sample. So again, this cannot be the reason for the bouncing on the nanospring arrays. Now the third possibility may be the high capillary forces. So when a droplet bounce is impact on the superhydrophobic surfaces, columnar surfaces, then mainly three pressure plays the role. One is the water Hammer pressure, then the dynamic pressure, and the capillary pressure, which is anti-wetting pressure. So for the bouncing behavior, this capillary pressure has to be higher than both the two other forces. So we calculated this capillary pressure, and we found that this capillary pressure was again similar to the slanted column, and was very less than the vertical column. So again, this cannot be the reason for the bouncing mechanism. So what our hypothesis is that the elastic property of this nanospring has a significant role in the water droplet, and the increase in the rebound time and the coefficient of restitution, or COR, of this sample can be explained if we consider the compression of nanospring structure by the droplet impact. So people have considered and studied water droplet as a two mass system with separated by a spring, where the spring constant is the surface tension of the water liquid, and when this water droplet impacts on the nanospring, it creates a coupled double spring system, and it can transfer sufficient energy to the nanospring and create a compression in the nanospring, and nanos on when and this and sufficient energy can be stored and repaid back to that droplet and can cause rebound. So this is our hypothesis, and so the relation between this velocity and compression is given by this equation. So with a higher velocity means higher compression, which may increase the rebound time. And the second is the energy, absorbed energy is also dependent on the ym square, is proportional to ym square. So high velocity means high energy of a high fraction of energy will be stored and will be supplied back on recoil. So the coefficient of restitution may increase with high velocity. And Kaneko et al. Also performed another measurement where they performed the tensile test on the single nanohelixes, and they found that these silicon nanohelix behaves as a spring and has significant elastic deformation. So that corroborates our hypothesis. And so in summary, we fabricated vertically standing silicon nanostructure arrays, nanospring by GLAD, and these nanostructure are made from same material but have remarkably different droplet dynamics. And the rebound time and COR was found to be higher for silicon nanosprings than vertical column, even when the rebound was observed for both the samples. And the restoring force of the nanosprings may be responsible for the rebound of the water droplet. So I would like to thank our lab members and the funding agency. Thank you.
Thank you, Dr. Samir, for finishing on time. So now we can take one or two quick questions. Any question? Okay, so I have one question regarding like this bouncing of this droplet from this silicon, these nanowires. So have you studied the different like droplet size and how it is changing this bouncing behavior?
Yes. So actually, we have not changed the droplet size, but the effect of different heights we have studied. So actually, we have there is a dimensionless parameter that is called Weber number. So everything we have calculated in terms of Weber number, which contains the droplet diameter also. So either we can change the droplet diameter or height. So we change the height and see how it affects the bouncing behavior.
Okay. Okay. Thank you very much for the nice talk. So now we have the next talk in line by Dr. Ankit Soni. He's from Department of Physics, IIT Delhi. And the title of the talk is Synthesis of Crystalline and Porous Nanostructures by GLAD-assisted PLD. So Dr. Ankit, can please share your screen?
Hello. Is it visible?
Yes, yes, it is visible. Please go ahead.
Good afternoon to everyone. I am Dr. Ankit Soni, a project fellow in the Department of Physics, working under the Professor J.P. Singh. I would like to thank the conference convener for giving me a chance to deliver a talk. I will be discussing on the synthesis of crystalline and porous nanostructures by GLAD-assisted PLD. Yeah, so outline of the talk is introduction and different synthesis techniques. Then the material on which I have worked is a zinc oxide. Then I would like to discuss experimental setup geometry for GLAD-assisted pulse laser deposition system. Then effects of deposition parameters in doping, and at last application as a ultraviolet photosensing. As we know, nanostructures are the nanostructures having dimension, one of the dimensions between 1 and 100 nanometer. And the study and technology which encompass and such dimensions of structures are known as nanoscience and nanotechnology. And the most important features of nanostructures are low dimensions, that is size effects, large surface to volume ratio, and boundary effects due to the reduction in size. Until now, there are many nanostructures have been fabricated using various synthesis techniques. The picture on the right-hand side shows different types of nanostructures such as nanowalls, nanowires, nanorods, and so on. And there are different synthesis techniques. So these nanostructures can be synthesized by three different techniques, such as physical vapor deposition, chemical vapor deposition, and chemical solution-based methods. So in my case, we have used physical vapor deposition. That is, we have used the pulse laser deposition system over here, and have utilized a glancing angle deposition technique to go the nanostructures of zinc oxide. The principle of GLAD, I will not be discussing about this because already most of the people have discussed about this. And so the GLAD advanced GLAD processes includes like pre-deposition treatment, that is substrate seeding, controlling substrate motion and temperature, GLAD co-deposition, sequential GLAD, external staining, and post-deposition treatments. So in our case, we have used a pre-deposition treatment, that is substrate seeding. We have used zinc oxide as a material for the growth of nanostructure due to its novel optoelectronic applications. It has unique properties such as direct and wide band gap of 3.37 electron volt, which lies in the UV range, so which makes it applicable for ultraviolet photosensing applications. It also has high thermal conductivity, strong sensing of surface activity, due to which it can be used as a gas or chemical sensing applications. So some applications of ZNO includes like transparent thin film transfers, light emitting diodes, smart windows, solar cells, gas or chemical sensors, and ultraviolet photodetectors. On the left hand side, there is a hexagonal Woodside crystal structure of ZNO, where each zinc ion is surrounded by tetrahedron of 4 oxygen ions and vice versa. So motivation behind this work is basically most of the synthesis methods uses some sort of catalyst for the growth of nanostructures, like chemical methods or any other method. So which may degrade the crystalline quality of the nanostructures, and eventually it also hinders the performance of the device. Whereas in pulse laser deposition system, the nanostructures grown by these methods have high crystallinity to other methods, and also provides a defect-free nature, which is very important for the UV photo detection application. The second thing is high surface area to volume ratio, which is very important for gas and photosensing application. And moreover, if you use GLAD technique, so it aids the porosity in the sample, which actually provides the adsorption sites in the nanostructure for efficient gas and photosensing application. Next is this technique has more flexibility on the shape and size of nanostructures, so that the PLD parameters can be tuned, and we can design and fabricate the nanostructures of requirement. So the experimental setup of GLAD assisted PLD. So the figure on the top represents the typical setup of PLD, where there is an excimer laser, and in front of that we have a deposition chamber where nanostructures has been performed. In our case, we have used two stage for the growth of nanostructures. In stage one, the seeds of the target material were prepared by keeping the target and substrate parallel to each other. And in stage two, the nanostructures has been fabricated by tilting the substrate at an angle of 85 degrees. And with this method, we have fabricated the nanostructures by varying the different deposition parameters. The first is oxygen partial pressure. We have oxygen partial pressure in a range of 7.5 Pascal, 10 Pascal, and 15 Pascal. And these SEM images clearly reveal that the oxygen partial pressure has significantly affected the growth and morphology of the nanostructures. Initially, the nanostructure at low oxygen partial makes a beach-like structure, and at high oxygen partial pressure, it makes kind of nanostructures. So this difference in the growth and morphology of nanostructures is basically due to the difference in kinetic energies of the ejected species. On the right hand side, the XRD patterns reveal that all the nanostructures have preferential orientation along 002 axis, which represents the C axis and the vertical growth of the nanostructures. More importantly, these nanostructures show highly suppressed visible emission as confirmed from the photoluminescence study. So we can see that the two samples, representative two samples, we have tested the photoluminescence. So all the two samples have near band emission around the UV range and highly suppressed visible emission. So this visible emission is basically due to the various types of defects present in the zinc oxide, such as zinc vacancy and oxygen vacancy and so on. So in the present case, it is clear that the defects has been highly suppressed. So it revealed that these nanostructures can be used as UV photosensing applications. In the second study, we varied the seeding angle in the first stage of deposition. So seeding angle was varied from 0 degree to 75 degree, and the glancing angle has been performed in the second stage. So it is clear that at all the different seeding angle, the morphology has been significantly affected. And the XRD patterns again show that all the nanostructures are preferentially oriented along 002 axis, revealing the C-axis growth. And on the right-hand side, the crystallite size, FWHM, and the intensity ratio has been calculated. So it shows that with increasing the seeding angle, the intensity ratio has been changed. So it shows that with changing the seeding angle, the crystallographic orientation also changes. And in the next study, we have used different types of substrates and observed the growth of nanostructures. So we have used over here two crystalline substrates, that is sapphire and MgO, and one amorphous substrates, that is quartz, in order to compare the growth of ZNO nanostructures on crystalline as well as amorphous substrates. So XRD patterns reveal that again, the nanostructures are preferentially oriented along 002 axis, that is C axis. And if we zoom this 002 axis and calculate its WHM and crystallite size, so it shows that the nanostructures which are grown on sapphire substrates have higher crystallite size and less WHM. So which represents that the nanostructures which are grown on crystalline substrate, that is sapphire, have more crystalline nature as compared to the other two substrates. So these FCM images show the growth of nanostructures, and AFM images well corroborates with the AFM images, SEM images. It is clear that the nanostructures which is grown on sapphire substrate have different growth and morphology as compared to the other two substrates, and the growth on the two crystalline substrates, that is sapphire and MgO, is the difference in growth on ZNO on these two substrates is basically due to the difference in lattice mismatch between the substrate and the ZNO seed layer. Using these nanostructures, we have fabricated ultraviolet photodetector and measured the photosensing using UV light. So the schematic on the left-hand side represent fabricated UV photodetector, and on the right-hand side, the schematic of the experimental setup. So this setup also has provision for measuring the photosensing in presence of vacuum and other gases. This slide represents the IV characteristic and photoresponse characteristics of the nanostructures grown on different substrates. So IV characteristics represent that all the nanostructures, the nanostructure which is grown on sapphire substrate have a very minimum dark current, that is around 0.14 nanoampere, and the highest dark current has been observed for the sapphire which is grown on, for the ZNO which is grown on quartz substrate. So the difference in dark current is basically due to difference in porosity. As we can see that the sample which is grown on sapphire substrate has maximum porosity. So the maximum pores basically provides the more adsorption sites to the oxygen molecules, and which reduces the dark current and enhances the sensitivity of the sample. The photocurrent characteristics has been measured using the UV light 365 nanometer by UV on and off. So why this photocurrent photocurrent increases and decreases by UV on and off? So I'll be explaining in this slide. So the sensing mechanism is basically governed by the adsorption and desorption dynamics. So to understand this, let us take the first cycle of the UV photocurrent, current versus time. And suppose this is the ZNO nanostructure. So in ambient condition, what happens? The ZNO, the free electrons is basically captured by the surrounding oxygen gas molecules, and it creates depletion region over the surface of the nanostructures due to the adsorption process. The mathematical form of the adsorption process can be written, can be explained as follows, which is representing the region 1. And now what happens when we shine the UV light? There is a generation of electron hole pair. So by which this hole is basically combined with the adsorbed oxygen and makes the oxygen free in that environment. And in this way, the electron is free for the conduction. So this process is known as photodesorption process, representing the region 2. Now again, if we switch on the UV light, the adsorption takes place. So by switching on and switching off UV light, the photocurrent multiple illumination and UV off, the photocurrent cycles can be observed. So this table represents the comparative performance of the present photodetector and other photodetectors fabricated by different methods. So it represents that the rise time and decay time have similar values in the range of seconds as reported by the earlier literatures. In the next study, we have used gallium as a dopant in ZNO nanostructures, and the XRD patterns reveal that the nanostructures, undoped and doped nanostructures, again have predominant crystalline plane along 002, that is C axis.
Please wind up in maybe 1 minute.
Yes, sir. Sure. And Raman study again confirms the Woodside structure and the successful doping of the gallium into the ZNO lattice. The surface morphology again reveals the variation in the surface morphology and the growth direction. In order to study the visible blindness of this photodetector, we have performed this measurement under 3 different lights, that is red, green, and blue. So it is clear that there is absolutely no response in the red and green light, while there is a small response in the blue light, which is comparable to the dark currents itself. Whereas we compare the blue response as compared to the UV, there is a huge difference for both of the samples. And we have also tested this photodetector at low temperature, that is at 10K, and compared the results with room temperature results. So it is clear that the detectors are well performing even at the low temperature. So this represents that the detectors can be used as a low temperature application, such as space applications and other applications also. So the highlights of the work is like the grown nanostructures, so crystallinity, they are defect free, they are visible blindness. And they also show porosity due to the glancing angle deposition technique, and due to their vertical nature, they are also applicable for ultraviolet sensitive applications. So all these properties makes them applicable at diverse environmental conditions. So I'd like to acknowledge my PhD supervisor, Professor Krishna R. Mawani, IIT Indore, and my group members. I also would like to acknowledge my current supervisor, Professor J.P. Singh, IIT Delhi, and all group members of GLAD and Nano CVD lab. Thank you.
Thank you very much, Dr. Ankit.
Thank you, sir.
Now it's time for a quick one question from audience. Anybody has any question? Yes, Sasank, please go ahead.
Okay, yeah, Ankit, nice work. So I just want to ask, you have used GLAD technique for the porosity of the substrate, like nanostructures. So it was it on the only purpose to use the GLAD, or you can use other technique for the same purpose? For the application point of view?
Yeah, especially for application point of view, we deliberately created the pores using this GLAD technique. Otherwise, PLD is basically known as for thin film deposition. So if we use GLAD technique over here, so it creates the porosity. So that is the advantage of GLAD assisted PLD.
Okay, to enhance the surface area of the nanostructures also?
Right.
Okay.
Exactly.
Okay, thank you, Ankit.
Thank you, Shashank.
Okay, so there is no question. I have one quick question. So in your different substrate, when you are depositing this same material, so you observe a different type of a time response. So,
right, sir.
So what is the reason for that?
Yeah, the time response is basically due to the difference in this dark current. Basically, as I told you, the sample which is grown on crystalline substrates have very low dark current due to the higher porosity. So as low the dark current, the photo response will be higher. If we take the ratio of IP by ID, So ID is very minimum for this particular sample. That's why this IP by ID ratio is higher for more porous sample.
Okay. Okay. Thank you very much.
Thank you, sir.
Thank you. So in line, we have next talk by Dr. Sabyasachi Bandyopadhyay from All India Institute of Medical Science, New Delhi. And he will talk about surface enhanced Raman spectroscopy for the early detection of dengue antigens. Dr. Sabyasachi, please
Yes,
share
yes.
your screen.
Yeah, am I audible, sir?
Yeah. Please go ahead.
Yeah, thank you for your kind introduction. And before I begin, I would like to thank Professor JP Singh and the organizing committee of this Nano GLAD conference for giving me the opportunity to deliver a lecture. So the talk, what I will deliver today, the work I have done when I was in Professor JP Singh's group as a senior project scientist. And the title of the talk is, the topic of today's talk is surface enhanced Raman spectroscopy for the early detection of dengue NS1 antigen. Yeah. So yeah, so the introduction, the brief introduction about today's talk. As we all know, dengue is a mosquito-borne disease, viral disease, caused by dengue virus, DENV. And this is a common disease for tropical and subtropical countries like India. This dengue virus has 4 distinct serotypes, DENV 1 to 4, and they can cause 3 structural protein like capsid, membrane, and envelope protein, and 7 non-structural protein like NS1 and others. It has been shown that NS1 is the main antigen protein which is expressed when a person has dengue virus or dengue fever. So even if this is a very common type of disease, so rapid, specific, and on-site diagnosis of this viral disease at the early stage is still challenging. There are mainly 2 very robust techniques like ELISA and RT-PCR when people use to detect the virus inside human body. But the limitation is they are not very sensitive, they are time-consuming, they are complicated, and sometimes very skilled hand is required. And also these are not very high throughput. There are some other techniques like antigen and antibody based kits, which are mainly rely on the concentration of antigen or antibody like IgM and IgG. But the main problem of these kits, there are kind of false result may appear since these are rely on the concentration of antigens and antibodies. So to overcome this kind of problem or these limitations, we thought that if we have if we can develop a rapid, sensitive, and reliable bioanalytical method to directly diagnose the viral infection or the presence of virus or NS1 antigen inside human bodies, that would be really helpful. So here we have used glancing angle deposition technique, which is a physical vapor deposition technique. And using the GLAD technique, we have fabricated silver nanorods on glass substrate. And we have used Raman spectroscopy as a molecular fingerprint technique to detect the signature peak from S1 antigen. So, we have to get in and substrate on that carboxylic acid we attached then it has been conjugated, and after that SARS has been applied on that antibody antigen conjugated substrate. I will give the details, but before I go into details about my work, the idea we have generated in Professor JP Singh's lab, and the paper has been published by Dr. Sasank Ghalot. He is the former in Professor JP Singh's lab. What he have used, he have done the work where NS1 antigen he have deposited, he have physi-absorbed on silver nanorods. The silver nanorods, as you can see, the substrate where he has prepared by GLAD deposition technique, and after preparing the substrate, he has physi-absorbed the NS1 antigen as well as diluting the NS1 antigen with FBS and physi-absorbed on the substrate. When he has done the Raman spectroscopy using these handheld handheld Raman spectrometer, what we got from TSI Inc. USA. Using this handheld Raman spectrometer, he got this spectra, and he has shown that when there is the concentration, NS1 concentration is there are two unique peak he has shown. One is 1005 centimeter inverse, one is 1395 centimeter inverse. And when this NS1 is diluted with FBS, these two peaks are deleting out or going off. So he has done this work first in the lab using commercially available NS1 antigen and by physiadsorption on the substrate. After that, he has used the actual serum sample from patients. He has used healthy control subject as well as NS1 negative subject, the person having the fever but NS1 negative, as well as NS1 positive subject. So using these three subjects, when he has done that physiadsorption technique on the GLAD substrate, he got this kind of spectra, and using a statistical analysis, the principal component analysis, he has shown that these healthy control NS1 positive and NS1 negative, they are completely clustered and they are separately represented in this principal component analysis diagram, and they can say that which one is healthy control, which one is NS1 positive, which one is NS1 negative. So it was a very robust and very reliable technique, but the only problem is, as we realized, this is a non-specific kind of absorption. So if we can absorb or if we can attach NS1 on the substrate very specifically using NS1 antibody, so it may be more confident, it can be more confident, and maybe the non-specificity can be decreased. So with that idea, first we have prepared the GLAD substrate, search substrate using the glancing angle deposition technique. The substrate was prepared like this, where on glass surface we have prepared 20 nanometer titanium adhesive layer. On top of that, 200 nanometer silver film. On top of the silver film, 1 micron silver nanorod. This is the scanning electron microscopy image. This is 1 micron scale. This is in 200 nanometer scale. As well as we have, along with the same image, we have characterized with EDX spectra, absorbance spectra. In absorbance spectra, we are getting 450 nanometer and 500 nanometer peak, which is the indication of the presence of silver nanorod, as well as X-ray diffraction pattern we have seen, which indicates the silver nanorods are synthesized on the glass substrate. After getting those 6 silver nanorods, we have attached 3 mercaptopropionic acid, and we have produced a self-assembled monolayer on it, where you can see that carboxylic group at the top end of that SAM. After doing that, after attaching those carboxylic group, we have used very well-known carbodiimide cross-linking chemistry, which is actually EDC-NHS chemistry, to prepare NHS ester on this carboxylic group. So we have treated it with EDC as well as NHS. So this NHS ester has been prepared, which is very stable, and this is actually amine reactive group. When primary amine will come and will conjugate with it, so it will produce a very strong amide bond, and using this EDC NHS coupling chemistry, we can attach antibody on this NHS ester. But before going to show the antibody attachment, I want to give you a brief idea that how this NHS ester formation on top of the GLAD substrate, on top of the search substrate, we have characterized. So first we have characterized the carboxylic acid using Renish or Raman spectrometer in our lab, using 780 nanometer laser with 50x objective and 1% laser power. And we got, there is a stretching of CCO as well as symmetric and asymmetric stretching of carbonyl, indicates that carboxylic group is there. And after getting the NHS ester, these carboxylic symmetric and asymmetric stretching are off, but we are getting new CCO. This may indicate that NHS ester is present. Although for our actual work, we didn't wash out the NHS ester. After forming the NHS ester, we directly added the antibody on it. I will give you the details. But before going to the antibody work, we wanted to check whether the amine and carboxylic acid coupling after NHS ester formation is working or not. So what we have used aniline, and we have attached it on NHS ester. And after doing that, after forming these aniline amide bond substrate, we using the same Renish, using the same parameters, we have shown that these aniline has been attached on carboxylic acid SAM. If you can see the green spectra, the bottom spectra, where on silver nanorod, we have at physics of 1 molar aniline, and it is giving some signature spectra of aromatic ring. After attachment with EDC NHS coupling, this is for this blue one is for 10 millimolar EDC NHS coupling, this is for 100 millimolar EDC-NHS coupling, it is showing that these signature peaks are present on EDC-NHS coupled aniline. So it indicates that EDC-NHS coupling of carboxylic acid and amine has worked well. And after confirming this thing, we goes for attaching antibody on these NHS ester modified carboxylic acid SAM. Here you can see the antibody has the antigen antibody antigen capturing region. So this is the epitope and paratope region where antigen can come and attach. And on that antigen antibody capturing region, you can see the amine are present. Go and can attach here, and carboxylic acid group are at the bottom. But since these antibodies are a complex structure, so we don't know how exactly it will go and it will attach here. So we tried to see this method that whether it is working well or not. So for that, we have used 0.5 microgram per microliter concentration of NS1 antibody, and we have attached this NS1 antibody into this carboxylic acid SAM, and producing those antibody are attached by amide bond, as I have already shown, using EDC-NHS coupling. After getting this amide modified antibody, after attaching the antibody on this substrate, we have added antigen, and we tried to get the spectra of this antibody attached as well as antigen attached spectra of this substrate. So what the method we have used, first we have prepared the carboxylic acid SAM. After that, we have used 10 millimolar EDC-NHS coupling, and on top of that, on top of EDC-NHS on top of the NHS ester, we have used 0.5 microliter NS1 antibody, and on top of NS1 antibody, we have attached NS1 antigen with two different concentration. One is 0.5 microgram per microliter, another one is double dilution with deionized water, which is 0.25 microgram per microliter. So for that, to get the Raman spectra, to get the surface NS Raman spectra on that gold substrate, gold nanorods substrate, we have used the same Renishaw spectrophotometer using the same parameters. We got the spectra. So in the left side, we can see the full spectra. Here you can see the bottom one, which is the EDC-NHS after the antibody attachment for 2.4 hours attachment only. After that, we got the 20 hours attachment, just one night we keep the antibody with that EDC-NHS coupled substrate. And after the antibody, we got the antibody spectra with the antibody. We have attached the antigen with two different concentration. One is for 0.5 microgram per microliter, one is with double dilution 0.25 microgram per microliter. And this is the zoom-in spectra. So in these Renishaw, using the Renishaw, the search spectra, we have seen there are mainly for antigen spectra for this yellow and blue one, we have seen that there are 4 peaks, 403, 420, and 850 and 871. They are uniquely appearing with this Renishaw instrument. But ultimately, we are not using Renishaw instrument. We have a portable Raman spectrometer, what I have already shown that Dr. Sasank has used. So these Raman spectrometer, portable Raman spectrometer, we will use what he has used, and he has shown there are 2 unique peaks, 1005 and 1395 centimeter inverse. So we have ultimately used this portable Raman spectrometer for the same kind of substrate what we have done here. So after getting the Renishaw result, we have taken the search spectra of the same substrate after attaching antibody and antigen on it with the that handheld Raman spectra. And this work has been done by Ms. Sarjana Jadhav. She is currently working as a PhD student in Professor Singh's lab. And when she got the spectra, very interestingly, we have seen, you can see this is the EDC-NHS spectra, the pink one. After antibody attachment, this is the blue one. And the black one and red one are the NS1 antigen spectra. The black one is where NS1 antigen is diluted with hemoglobin, and red one where NS1 antigen is diluted with deionized water. Very interestingly, using this handheld Raman spectra, we have seen this 1010 centimeter inverse and 1405 centimeter inverse peak here for these antigen bound species, antigen bound substrate, and it is showing that this kind of peaks for NS1 antigen is coming here, although this spectra is the average of only 5 spectra. So we are going to get more spectra for more different substrates using the same kind of methodology, using the same kind of substrate, NS1 antibody and antigen at a substrate, and we will do more spectra. We will collect more spectra using the handheld Raman. After confirmedly pick this spectra, we will do the FBS dilution thing, means fetal bovine serum dilution thing, as Dr. Sasank has done before, and we will get the spectra. After getting those spectra, we will go for clinical samples, actual sample from dengue virus patient or the patient having dengue fever. So that is our final goal, and from that clinical sample, we will do the same experiment using the same kind of substrate. So you can see these two peaks as I already have mentioned. So this is the conclusion where we have first prepared silver nano rod where it has been fabricated using GLAD technique and we have used it as a search substrate. 3 markaptopropenoic acids and we have prepared where carboxylic group are there at the top and EDSC NHS carbodiamide coupling we have used to attach the NS1 antibody on it. So NS1 antibody was conjugated first on the search substrate and after that NS1 antigen we have conjugated on it. Further, we will go to get the data from dengue patient. SARS have been used for fingerprint intended to detect the signature peak from NS1 antigen. And finally, for using handheld portable field deployable Raman spectrometer, we have shown that we can rapidly detect the NS1 antigen on SARS substrate. So I would like to thank Professor Jitendra Pratap Singh for giving me the opportunity to deliver a talk in such a kind of a very prestigious platform. I am really thankful to Sarjana and Sasank for helping me out to make the presentation. I am thankful for all my group members, to IIT Delhi, to Imprint Project, and to Ministry of Health and Family Welfare for funding. And thank you all for your kind attention.
Thank you, Dr. Sabyasachi. So now we have time for one quick question. Yeah, Shashank, please go ahead.
Yeah, hi Sabyasachi.
Hi,
very
Shashank.
nice talk.
Hello.
So,
Thank you.
I just want to ask, you have used 3-MPa for the binding of antibody. So you are saying that it is the self-assembled monolayer of 3-MPa on top of the AG nanorods. So how did you confirm it, whether it is the SAM layer? And if it is not SAM layer, then how is going to change the result or search spectra?
Yes, thank you, Sasan, for the question. So yes, so after preparing the self-assembled monolayer, since you are seeing that it is we have prepared it in ethanol solution, mainly in 1 to 2 millimolar ethanol solution. So after preparing the SAM, we have washed it out thoroughly with ethanol as well as in water. After that, we have the search spectra. Symmetric and asymmetric stretching we are getting. So even if after multiple washing, this kind of spectra we are getting. So from that we can confirm that the carboxylic acid group are present on the substrate. So if it is just a physi-adsorb, so after multiple washing with ethanol, it should go off. It will not be present on the substrate.
So you want to say that it is the monolayer, or it can be the multiple layers of this molecule?
Yes, that is it is difficult to say at this point whether it is monolayer or multiple layer. So there is a possibility that multiple layer could be found. Yeah. True.
Okay. So, and one more question, that after drop casting the antigen on top of the antibody, so there is a highly probable chance to get the spectra from all the layers, like EDC, NHS, antibody, and the amine group from for this purpose you are using.
Yes.
So, is it not difficult to separate out these noise or something, you can the background signal?
True. So the thing is that this is also a very good question, because if you see the spectra here, it is really a complicated spectra. So there are so many peaks they are coming. So it is difficult to analyze each and every peak. So what is our target? We wanted to see some unique peak which is coming from NS1 antigen. So if you see this spectra here, if you see here what we are getting, we are trying to get the unique peak as you have shown previously. So in your spectra also, if you see there, it is a complicated spectra. It is difficult to analyze each and every peak. So definitely it's complicated. So our target is to get some peak which is uniquely present after attaching NS1 antigen on the antibody. So if it is not coming, so then probably we have to think of in other way, that how we can modify our device. So that's why I have said, so since it is an average of 5 spectra, so here we are seeing some peaks which are unique for this antigen, but we cannot confirm it right now. We have to have more data to confirm it. So then we can we cannot analyze all the peaks from this spectra, but what we have to see, we can concentrate on particular couple of or 3 or 4 peaks.
Yes.
Yeah. So that we can do actually.
Yeah, thank you. Yeah, nice suggestion. Thank you.
Welcome, Susan.
Thank you very much, Dr. Sabyasachi.
Thank you, sir.
Now, this session actually is, we will have the break now, and I would like to thank you again for all the speakers who has given a wonderful talk. And now over to you, Shashank.
Thank you, Professor Mukesh Kumar, for chairing this session. So now we have almost 1.5 hour break, and then we are going to meet at 5:15 p.m. for group photo session. So please make sure you will be there by turning on your camera, so we can take the picture screenshot. So please be there on time. And next speaker will be Professor Ishan Burman at 5:30 p.m. So thank you so much. Okay.
Thank you. See you all.
So hi everyone, welcome back to the International Conference on Sculptured Thin Films. I hope all of you are doing well. So now we are here to take a group photograph for the conference. So I request you all to be still and yes, so I will take multiple pictures to cover all of you. So please turn on your camera, all of you. Some people are not seen on the screen.
A large public garden is called the park olur değil mi?
Your voice is not audible.
Yeah. So thank you all of you. I have tried to cover all of you here. If somebody is missing, then we will ask via email to send us the picture and we will put there. Thank you so much. So now we will start our session. Actually, the schedule time is 5:30. So if our speaker and chairperson is here, then we can introduce them.
Yeah, I think Professor Burman is already here. So So
Okay, can we start?
You can invite Mukesh for chairing.
Yes. Okay, sure. So I would like to request the chairperson of the session, Professor Mukesh Kumar, on the stage to introduce the next speaker, Professor Burman. So over to you, Professor Mukesh.
Sure, Shashank, and welcome to this session. So we have two invited lecture in this session. The first lecture is by Professor Ishan Burman. He's associate professor in the Department of Mechanical Engineering at Johns Hopkins University with an joint appointment in the Department of Oncology and Radiological Science. He is also a senior investigator of National Institute of Health. He graduated from IIT Kharagpur and then he moved to MIT for his PhD and postdoctoral work. Dr. Burman established his independent group at the Johns Hopkins University in 2014. His work has been extensively published in peer-reviewed journals like PNAS, Nature Materials, Advanced Materials, Cancer Research, Anglicam, Chemical Science, Nano Letters, and other high-impact journals. Also, he has been prominently featured in leading scientific and popular media like Wall Street Journal, CNN, etc. He has received numerous awards for his research contribution. So I welcome you, Professor Ishan Burman, and he's going to talk about on self-assembled intracellular Raman reporters and plasmonic nanocavities. So over to you, Professor Ishan Burman.
Thank you so much. Hello, everyone. Let me try to share my screen first, and then we will get started. I don't do Cisco WebEx much, so this might take me a minute to figure it out. Can you see my screen?
Yeah, it is coming up. Yeah.
Yep. Great. Thank you. Hello, everyone. Good morning, afternoon, and evening, wherever you are. It's a pleasure to share with you some of our recent work in two distinct areas in designing self-assembled intercellular Raman reporters and in fashioning plasmonic nanocavities. But before we go forward, let me thank the organizers of this conference for putting together a wonderful meeting in these difficult times and also inviting me to talk about our work. I'm an associate professor of mechanical engineering with joint appointments in oncology and radiology at the Johns Hopkins University. I also am part of the leadership team for the Laser Biomedical Research Center that's housed at MIT. The first work that I'm going to talk about is motivated by the need for better theranostic imaging with the goal of creating multimodal nanoprobes for in vivo tumor assessment and ablation. The other area stems from a long-standing interest we've had in developing plasmonic constructs for single molecule measurements, label-free and reproducible. Difficult, but not quite impossible, as I hope to convince you by the end of this short discussion. Our broad research interests reside in engineering innovation at the interface of biophotonics, nanomaterials, and machine learning for analysis of complex biological systems, as is required to address questions important to both fundamental biology on one hand and applied clinical research on the other. One of our main workhorses is Raman microscopy, which serves as a bridge between chemical and morphologic analysis at the cellular and tissue levels. Here I show you the first compositional maps that were acquired in our laboratory of hemoglobin and the malaria pigment hemozoin in live functional red blood cells infected by the parasite Plasmodium falciparum. This kind of imaging offers fresh insights into the formation and packing of hemozoin that has important implications for drug development. We're also deeply engaged in the development of surface-enhanced Raman spectroscopy, or SERS tools, that can offer rapid, accurate, and convenient measurements of blood-based biomarkers, as well as perform single-cell analysis. On the left here, you can see we create mechanical trap-based platforms and also generate ultra-thin graphene nanoparticle hybrid skins for capture and 3D molecular profiling of single live cells. Inner surfaces of these structures are dotted with plasmonic nanoparticles that enhance the Raman signatures of membrane constituents. On the right here, you can see a furin-targeted magnetic resonance and Raman detectable probe. So essentially a multimodal probe that we reported last year in Nature Materials, which allows imaging of tumor aggressiveness, drug accumulation, and therapeutic response. But before I start, let me acknowledge those whose work forms the foundation of today's presentation. I have the privilege of working with a number of wonderful graduate students and postdoctoral colleagues. I actually learn a lot from them. In particular, I'll showcase some of the work performed by Dr. Debadita Paria, an outstanding experimentalist with an equally first-rate analytical mind. Doctors Le Liang and Pang Zhang are top-notch material scientists in my group. Some of our recent alumni have also contributed to these studies, including Dr. Shomik Siddhanta, who has launched his independent program as an assistant professor at IIT Delhi. Of course, our collaborators at Johns Hopkins and elsewhere around the globe have made major contributions to these studies. Finally, I'd like to acknowledge our funding sources for their generous support of our work. So why Raman? In biology, imaging is a major driver of discovery. Richard Feynman had once famously said, "It is very easy to answer many of the fundamental biological questions. You just look at the thing." 60 years later, dramatic improvements, particularly in fluorescence imaging, allow us to visualize increasingly smaller structures, view specific molecules inside cells and tissues, and study their dynamics. Yet, labeling may perturb the function of a molecule and limits the capacity of discovery as it is applicable only to known species. But you have to wonder, could we perform the same quantitative imaging without using any labels whatsoever? Raman microscopy, which uses inelastic light scattering to probe vibrational modes of molecules, enables multiplexed chemical fingerprinting in live unstained biological samples. Hence, in our various thrusts, we seek to leverage this emerging approach for single cell analysis, for spectral pathology, and to monitor treatment response. As you are likely aware, Raman spectroscopy is a fundamental form of molecular spectroscopy that is widely used to investigate the structures and properties of molecules from their vibrational transitions. What makes Raman spectroscopy stand out is its exquisite molecular specificity. Here, on the top right, I show you the Raman spectrum of cholesterol, for no particularly good reason, except that it exhibits the characteristic steroid ring vibrations as well as a number of sharp bending and stretching modes. Bottom line, you have a lot of information content. Raman spectroscopy, of course, has come a long way in the last couple of decades. Several biomedical applications of Raman spectroscopy have been reported. For instance, this relatively recent publication in Science Translational Medicine reports on live local detection of cancer cells in the human brain. This Raman-based probe enabled detection of the previously undetectable diffusely invasive brain cancer cells in patients with grade 2 to grade 4 gliomas. I'm sure you appreciate that is an extremely challenging proposition. For many of our investigations, we actually use Raman spectroscopic imaging because it does not require dyes or labels, allowing us to probe the composite biomolecular information rather than interrogating a small set of suspected molecules. It offers real-time information in a non-perturbative manner, requires minimal sample preparation, and does not use radiation. While we love the molecular specificity of Raman, the problem is that you often only get a handful of photons to play with. Surface enhanced Raman spectroscopy, or SERS, is a surface sensitive technique that enhances Raman scattering of molecules adsorbed on rough metal surfaces or on nanostructures. The quantum of enhancement primarily depends on the localized surface plasmons on the noble metal nanoparticles. Because excitation of the localized surface plasmons, or should I say LSPR, lies at the heart of SERS, our improved and continuously improving ability to control the surface characteristics has taken SERS from a somewhat esoteric phenomenon to a reliable analytical tool. Indeed, nanoparticle enhanced assays have recently exceeded fluorescence detection limits and that of conventional immunoassays while being quantitative over a wide range of probe concentrations, providing a potential opportunity to quantify spectroscopically multiple epitope concentrations in small volumes. My internet connection seems to be a little bit spotty. I'm going to see if I can stop my own video and if that helps matters a little bit. Uh, let's see here. Yeah, I can't seem to figure out. Unless we'll move forward. A major advantage of Raman imaging here, as you can see on the top panel, is that it can give spatial information about various chemical constituents in a functional cell rather than relying on bulk or fractionated analysis of extracted components. With the overarching goal of elucidating intratumoral heterogeneity, that is, heterogeneity of cells within a tumor, we've partnered with the David Gracias laboratory at Johns Hopkins itself and created these mechanical trap-based platforms for capture and 3D molecular profiling of live cell surfaces. We fabricate these passive single cell grippers whose inner surfaces are dotted with plasmonic nanoparticles, as I hope you can see here, that enhance the Raman signatures of membrane constituents. The energy required to actuate these grippers is derived completely from release of residual stress in these 3 to 27 nanometer thick films. So there's no active components here, no batteries, no wires, no tethers, nothing of that kind. Next, by leveraging the functionalization of the inner surfaces of the mechanical traps with the plasmonic gold nanostars and exploiting the conformal contact of the plasma membrane, our platform enables non-perturbative acquisition of SIR spectra of the plasma membrane constituents. Here, for instance, is a 3D Raman image, a reconstructed 3D Raman image of a drug-coated microbead that is held by the trap, which shows a very close, I would say, a remarkable resemblance to the corresponding SEM image. We've now, of course, moved away from the microbead, which is interesting, but not particularly so, onto actually doing cellular cell surface imaging. Next item on the menu today, graphene wraps. We have recently engineered an ultra-thin graphene nanoparticle hybrid skin that is thermally responsive and can be triggered to self-fold and wrap around 3D microobject in a highly conformal manner owing to its superior flexibility. Graphene, as you all know, provides an atomically thin monolayer structure with good chemical inertness, biocompatibility, and extremely low bending rigidity. Here, graphene is combined with silver nanocubes that permits strong plasmonic enhancement. The other critical piece here, I hope you can see, is the grafting of the so-called PNI PAM brushes on the graphene that endows it with a unique temperature responsive self-folding capability. So if you raise the temperature by a couple of degrees, it tends to fold around itself, as you can see here. Here you can see our skin successfully wrapping a spiky pollen particle, thereby allowing acquisition of high resolution Raman maps. Suffice to say that conformal contact with this kind of a spiky pollen particle is, well, next to impossible to achieve using hard, rigid surfaces. These platforms then provide a portal for extended eavesdropping into the inner lives of these cells. This, of course, is the confocal Raman maps and a z-stack of the same, and you can use this to reconstruct a 3D Raman image. A different embodiment that has received considerable attention in the broader search community is in the point of care diagnostic space, and that is of labeled search probes. So thus far, we are talking of label-free search. Now we are talking of labeled search probes. Labeled search probes typically contain the nanoscale metallic structures and organic molecules that act as a quantitative reporter for the presence of the probe. The signal of this reporter is greatly enhanced to transduce biochemical species of interest at the molecular, cellular, and tissue levels to measurable signals. An embodiment of such nanoprobes is shown here with different targeting moieties, such as these antibodies. The different Raman signatures of the reporters allow us to visualize the molecular expression levels and the distribution in tissue as well as in serum assays. The quantitative expression levels, as you can see here, can then be employed to provide, for instance, a prognostic score for personalized medicine. Our philosophy here is very simple. It is to use routine Raman spectroscopy, which will be useful in scaling down and making the eventual assay cost effective, and concentrate instead on engineering robust nanoparticle probes with ultra high sensitivity. A particular application of interest is in developing liquid biopsy tools that can offer robust and sensitive measurements of circulating biomarkers with minimum touch points, turnaround time, and operator expertise requirements. In our first generation design, as you can see here, we use similar capture and detection concepts to recreate an ELISA-like sandwich assay, except with higher sensitivity and no fluorescence quenching. Here, the SIRS nanoprobe has a gold nanostar core, a layer of Raman reporters, as you can see from these green dots, and finally a silica shell that affords facile surface functionalization. We tested a panel of 3 serum-based tumor markers, CA15-3, CA2729, and CEA, which are significantly overexpressed in patients with metastatic breast cancer. As you can see, when there is no tumor antigen, well, there is no signal. While in the presence of one, there is an extremely strong SIRS signature. As to its sensitivity, we've established limit of detection in sera for each of these tumor antigen to a factor of 5 to 30x lower, not 5 to 30%, 5 to 30x lower than that obtained using ELISA. The further integration of fast Raman mapping and SIRS nanoprobes has enabled robust multiplex detection in less than 10 minutes and in less than 5 microliters of serum, allowing conservation of these precious samples. By scanning a Raman probe over this assay, as you can see by doing a raster scan process, you can see clear differences in tumor antigen content between the representative specimens acquired from a healthy human donor and a stage 4 breast cancer patient. In more recent work, actually, we've also reported a fully labeled free SIRS in a capillary platform. In other words, you perform measurements of fluid samples directly in a plasmonically active capillary tube, no biorecognition elements needed whatsoever, as simple as that. The enabling innovation here is the integration of our silver ink precursor fabrication strategy with standard capillary tubes, which allows highly sensitive label-free molecular detection in clinical samples drawn into and in contact with the nanoparticle-coated tube. As you can see from the receiver operating characteristic curve here, or ROC curve, we are able to accurately classify samples from patients with heparin-induced thrombocytopenia, which is a difficult to diagnose immune-related complication that often leads to thromboembolism. Given the limitations of extant platforms, we are fast-tracking this innovation through the translational pipeline. And here finally is my hat tip to the principal subject of the conference, i.e. GLAD. I wanted to feature one slide that shows our use of oblique angle deposition to create biosensing substrates. We reported a couple of years back the design of plasmonic nanostructures based on rationally structured metal dielectric combinations called composite scattering plasmonic nanoprobes, which we call CSP, to generate an integrated multimodal biosensing platform featuring LSPR and SIRS. Specifically, CSP configurations were proposed which have several prominent resonance peaks, enabling higher tunability and sensitivity for self-referenced multiplexed analyte sensing. We mounted the substrate, as you can see, with gold nanoparticles at an oblique angle with respect to the evaporant flux, about 87 degrees to the horizontal, in an E-beam evaporator for subsequent deposition of 10 nanometers of silica and 10 nanometers of silver. Deposition at an extreme angle, known as oblique angle deposition or OAD, ensured that the evaporant was deposited preferentially on the gold nanoparticles and no deposition took place in the geometric shadow region of the nanoparticles. Using OAD and thermal de-wetting, large area uniform and tunable CSPs were fabricated for label-free LSPR and SIRS measurements. These CSP prototypes were subsequently used to demonstrate refractive index-based sensing and very sensitive molecular analysis based on SIRS readouts. Okay, let me shift gears here a little bit. A couple of years back, in early 2019, we had been involved in an effort for characterizing self-assembled nanoparticles for better magnetic resonance or MR imaging and simultaneous tumor therapy. Despite the transformative potential, the translation of nanomedicine, I think it's fair to say, has proven rather challenging, with a recent meta-analysis revealing that less than 1%, Yes, you heard me right. Less than 1% of the injected dose reaching the targeted solid tumor following systemic administration. Our collaborator, Dr. Jeff Bulte, and his team have been studying intracellular self-assembly of small molecule drugs into these larger nanostructures, as it has proven to be one of the more effective strategies to increase the concentration of drugs locally and to prolong their exposure time, increasing sensitivity while minimizing non-target toxicity. The potential benefits of tumor-specific intracellular self-assembly has then prompted them to develop an enzyme responsive, as in a tumor-specific enzyme responsive, in this case furin, theranostic platform for tumor imaging and therapy. For this study, the anti-cancer agent olsalazine, also known as OLSA, was conjugated to the cell-penetrating peptide RVRR, leveraging a biologically compatible click condensation reaction. Single OLSA RVRR molecules were self-assembled into these larger intracellular nanoparticles by the tumor-associated enzyme furin, which also prevent them, as you can see, from being pumped out of the cell. The formed nanoparticles are readily detected using CEST MRI by virtue of the exchangeable OLSA hydroxyl protons, but more on the mechanism in a couple of slides. First, using fluorescence microscopy, it was confirmed that intracellular condensation actually occurs near the Golgi apparatus in cells where furin was produced. Subsequently, mice were injected with subcutaneously injected with high furin producing cells, HCT116, in the left flank and lower furin expressing LOVO cells in the right flank. Serial CEST MRI measurements were obtained over 24 hours to determine the time course of substrate uptake within the tumors. The OLSA CEST contrast was higher, as you can see on the left flank, for HCT116 compared to that of LOVO, but that is along expected lines. In the HCT cells, some maximum signal was observed at about the 2 hours. The anti-tumor treatment effect was also studied. As you can see from these plots, the OLSA RVRR, but not the control and not the OLSA alone, showed more effective inhibition of the tumor growth, presumably resulting from the enhanced intracellular tumor retention of OLSA in agreement with the CEST MRI results. This was great, right? Fantastic result, fantastic publication. But there was a more important question that I wanted to ask as a Raman spectroscopist, one that you can probably guess. While such smart strategies for intracellular self-assembly of nanoparticles as reporters have been investigated fairly extensively for other imaging modalities, the potential of organizing molecules into supramolecular structures to tailor Raman signals has been surprisingly underappreciated. Indeed, we could not find one single report that tries to do this, but does not feature a plasmonic nanoparticle. And of course, using a plasmonic nanoparticle runs the risk of uncontrolled aggregation and cytotoxicity. So we wanted to give this a shot. So here's what we have. As you can see in this color-coded image, we start with the single molecule OLSA that is in green, right? So that's the green stuff you see over here. A latent cysteine motif, CUS, and the 2-cyanobenzothiazole CBD structure for click condensation reaction. This is in pink. And RVRR, the cell-penetrating peptide, and the substrate used for furin cleavage, that is in blue. So the biocompatible click condensation reaction occurs between the exposed cysteine here and the 2-cyanobenzothiazole group, which of course this is the 2-cyanobenzothiazole group, and this of course is the exposed cysteine, resulting in the formation of hydrophobic oligomers, mostly dimers, which subsequently self-assemble into these larger OLSA nanoparticles. We've also synthesized a couple of control compounds with scrambled peptide sequences and another that was short of the CBT motif, and neither, of course, could produce the OLSA nanoparticles, which was verified through TEM measurements. But before we move on, I'd like to draw your attention to the presence of the CN group, the cyano group, which prior to the condensation reaction is here and therefore gives you a strong alkyl peak. But after the condensation reaction, well, it vanishes. So the formation of the cyclized product means that there is no such group. We want to exploit this. And as I said just a minute back, we'll exploit these differential Raman signatures to develop a new class of Raman reporters. There are a few obvious differences between OLSA RVRR and the final OLSA nanoparticles, but none more obvious than the Raman signature from the cyano group, which disappears post condensation in this so-called cell silent region that permits real-time monitoring and also localization of intracellular aggregation. So what did we do? We used our confocal Raman microscope to construct Raman maps of the examined cells. The top panel here gives you bright field and Raman images recorded from furin overexpressing HCT116 cells incubated with OLSA RVRR. The 1168 centimeter inverse signal corresponds to the OLSA nanoparticle, not the OLSA alone, but the nanoparticle, whereas the 1440 wave number signal corresponds to the CH2 bending mode from intrinsic cellular components. So we use this to essentially draw the cell shape, which is similar to what you see in the bright field image. Now the bottom panel shows composite Raman images of HCT116 cells without and with incubation of OLSA nanoparticle alone, right, untreated, and these two control compounds, which we call CTR1 and CTR2. And what do you see? You see a clear absence of OLSA nanoparticle signature, unlike what we saw here. This panel then plots the intensity values as the area under the curve, underscoring the significantly higher intensity that is resulting from the higher intracellular concentration of OLSA nanoparticle in the furin overexpressing cells incubated with OLSA RVRR. Finally, we wanted to evaluate the performance of the OLSA RVRR probes for in vivo tumor detection. We performed a proof of concept study to study SCID mice, that is immunodeficient mice, were subcutaneously injected with HCT116 cells in both the left and the right flank. When these tumors reached a volume of 200 millimeter cubed, either OLSA VRR, OLSA, CTR1, or CTR2 was injected intravenously in the mice, right? So 2 hours post injection of the compounds, when tumor accumulation kind of, we saw previously with CEST MRI that 2 hours post accumulation is when maximum tumor accumulation occurs. So post these 2 hour interval, tumors were exposed with a skin incision, and a fiber optic portable based Raman probe was used to scan this tumor region, as you can see here. To capture the tumor heterogeneity and potential variance arising from differential accumulation of OLSA nanoparticles in each group, spatially distinct Raman spectra from each specimen were required. We next trained separate binary support vector machines, SVN classifiers corresponding to this 5 set of comparisons, i.e. OLSA RVRR versus untreated, OLSA RVRR versus CTR1 versus CTR2, ... You get the picture. The developed SVIM classifier showed 100% classification accuracy for 3 of these comparisons. For the comparison with CTR1, 2 of the OLSA RVR, as you can see here, were unclassified, not misclassified, but unclassified. One of the cases with the comparison with untreated was misclassified, and 2 more were misclassified. Taken together, this corresponds to a correct classification rate of roughly 92% and a misclassification rate of barely 2%, clearly underscoring the detection potential of OLSA RVRR in these HCT116 tumors. What is perhaps even more interesting is that we can easily load it up further. We are currently exploring the possibility of multimodal measurements with Raman and CEST MRI that has rarely been attempted. We can also include plasmonic nanoparticles and other alkyl tags in the reporter to create SIRS and or advanced alkyl tag-based nanoprobes. Finally, furin and RVRR is but one of the several enzyme substrate combinations for which this can work. We are currently exploring other options focused on prostate cancer theranostic imaging. How am I doing on time? I think I have about 5 more minutes, right? So I'm going to go and talk about the final piece in this presentation, but before that, let me just drink coffee.
Better will be maybe wind up in 3 minutes so that we can have some time for questions.
Okay, I'll do that in 3. So I wanted to shift gears and pivot our discussion quickly to plasmonic nanocavities. Metallic nanostructures with nanometer gaps support plasmonic modes with an extremely small mode volume, as you can see here from the artist rendering. And this, of course, constitutes an attractive platform for ultra-sensitive detection down to the single molecule level. Now, these plasmonic hotspots, for example, can be used to have very strong search signatures, and then you can use those Raman features to resolve for the different gap contents, demonstrating the ability to monitor molecular dynamics at the nanoscale. I'm going to skip over the bottom panel in the interest of time, but I'm going to tell you what we wanted to do. Drawing on emerging concepts in DNA nanotechnology and plasmonic nanocavities, we engineered these highly precise and robust nanocavities that we call DNA silicified template for Raman optical beacon or DNA strobe by using silicified DNA scaffolds for spatial organization of discrete gold nanoparticles. Now, DNA silica hybrid structures have been previously shown to possess extraordinary chemical inertness and mechanical resilience that are not achievable on bare DNA origami structures alone, but that has not been used for generating well-defined plasmonic nanocavities. Our DNA strobe structure is specifically and initially assembled through hybridization of two complementary DNA strands that are respectively attached to the core and satellite structures. Despite the apparent conceptual similarity or the simplicity of DNA origami and DNA silicification, though, such a strategy is difficult to realize in practice due to the electrostatic repulsion. We overcome this problem using positively charged Tmaps molecules, which serves as a co-structure directing agent. Again, in the interest of time, I'm probably going to skip over some of the fabrication details, but I'm happy to take questions offline here. What I wanted to show is what we can do with this, right? So the study here centered on this approach was recently published in Advanced Materials, and I wanted to quickly highlight some of our findings. Success of the DNA silicification procedure was validated using SEM measurements of the ultra-thin silica shell that conformally encapsulated the oligonucleotide functionalized gold nanoparticle assembly. As you can see here, we have fabricated various hierarchical nanoassemblies with progressively increasing complexity and different sizes of gold nanoparticles, from gold nanodimers to core satellite structures to core satellite constructs, as you can see from these SEM images. The scale bar here is 100 nanometers. So, two important findings here. One of the first things we wanted to do was to evaluate the impact of neutral and acidic environments on the chemical inertness and structural stability of such structures. We used standard PBS buffer and as well as a solution with a pH of 6, actually a dilute HCl solution. And well, you can see the difference for yourself, right? Well dispersed colloids in the DNA strobe samples, but without DNA silicification, not as much. Very clear change in color. And in this DNA strobe samples, that is with silicification, you see barely any change in the absorption spectra, indicating that it remains very stable under a variety of pH conditions. Another point of interest naturally was to confirm whether the silicification process improves gap control. One can visualize here the gap condensation in this pair of representative SEM images in the bottom panel. A statistical analysis confirmed that the center-to-center distance was reduced by a little bit, but what was crucial is reduction of the size variation. This size variation reduced from roughly 7 nanometers to roughly 2 nanometers, suggesting a significant improvement in our ability to control the nanogap and therefore offer controlled yet extremely large plasmonic enhancement. And here is my final slide. So the real question is whether we can see molecular events at these plasmonic hotspots. And we believe the answer is yes. A here is an illustration of stochastic single molecule events at a specific time point. Here, one Raman active molecules flows in and out of the hotspot volume at a time, switching the surge signal on or off. Using a repurposed turf microscope for wide field excitation and single Raman band detection, we acquired Raman images around the plasmonic nanocavities. Note here that the x-axis is time. It's not Raman shift. So what I'm showing you is the time trace of the surge intensity fluctuation at such a hotspot. Panel C is standard surge images that were acquired with an acquisition time of 10 seconds, and the DNA strobe constructs were presented as blurred hotspots. Yet, by fitting the point spread function to a model function, the emitting center could be uniquely determined at the centroid of the fitting function, just like super resolution fluorescence or storm. The fitting process that we performed using Thunderstorm was repeated for hundreds of images, and what you see here is the spatial profile of plasmonic hotspots, revealing super resolution single molecule Raman microscopy, and this resolution is down to 20 nanometers. This work is still somewhat at the proof of concept stage, but that being said, we've repeated this for thousands of movies now and for hundreds of molecules, or maybe tens of molecules, and it seems to hold up very, very well. So we are excited about what this bodes for the future, but I'm going to take some of those questions, I'm sure, offline. So with that, let me wrap up over here. Thank you for your patience, and I'm happy to address any questions you may have.
Thank you very much, Professor Burman. So excited talk. So now the floor is open for a few questions. Yes, Shashank, please go ahead.
Hi, Professor Burman. It was really nice talk and excellent work. So I have a question. So how do you control the gap between the nanoparticles when you are doing silication? You have showed there, so to control the enhancement factor. So if you make it very close, then there is a probability to down the enhancement factor.
Good question, and actually this has a very simple answer. So we vary the number of base pairs of oligonucleotide, right? So we've done with 19 base pairs, we've done with 50 base pairs, and we can actually very precisely control the plasmonic enhancement. That's why we call this a programmable structure, the DNA stroke template, that is. So here, for instance, if I can show you, so if you vary the number of base pairs you have in terms of the oligonucleotide, you can actually precisely vary the gap between the core and the satellite, or between two gold nanoparticles, a dimer, and so on and so forth. And that was important to us, right? That is important because we want to get high enhancement, but we also want to get reproducible enhancement. You know, in the search community, it's been theorized. I'm getting a little bit of feedback, by the way. In the search community, it's been theorized that there's this search uncertainty principle, right? That you can get a very large enhancement, but you can't get a reproducible one. Or you can get a reproducible enhancement, but you can't get a very large enhancement, right? So we wanted to break down that search uncertainty principle by doing this. And I'll tell you this is the most reproducible enhancement I've seen in over a decade in this field. That's what makes me excited about probing this research direction further.
So have you calculated the enhancement factor in this case?
Yes. So we've calculated, and depending on how many base pairs we have, we go from about 10 to the power 7 to about 10 to the power 10. Our goal really was not to get the highest enhancement factor we could get. I'm guessing we can probably get even higher than 10 orders of magnitude. But we wanted to probe some of these other aspects, including, how stable is it? How reproducible is it? How chemically and mechanically resilient is it? And most importantly, can we see these single molecule stochastic events as these molecules go through these ultra small mode volumes?
So, Professor Wang.
Thank you, Professor.
Yeah.
Next question we have from Professor Wang.
Yep.
I think you're muted.
Please unmute.
Yeah. So can you hear me now?
Yeah.
Yes.
Please go ahead.
Yeah. Thank you. This is a very nice work. Fantastic. And so my question is, may you make a comment that what is the limitation the Raman spectroscopy going to have for the bio application, and how to cross this barrier?
Yeah. Wow, that's a good question, but an extensive discussion probably needs another hour. But I'll try and keep this very brief. So I think there's two aspects, right? One is if you're talking of fundamental Raman, spontaneous Raman spectroscopy, and then you have all these other variants, right? You have stimulated Raman, you have coherent anti-stoked Raman or CARS, you have surface enhanced Raman, and so on. Let me first talk about spontaneous Raman. So spontaneous Raman has actually gained a considerable bit of attention in the translational space, right? In the biomedical space, as for example, to be used as biopsy guidance techniques. So in fact, there's a couple of companies which are trying to push that frontier for using Raman to guide biopsy guidance in vivo. There's a couple of other companies which are using Raman for intraoperative tumor margin assessment. So in the surgical suite, when you take out the tumor, how do you know all the tumor cells have been excised? The entire tumor has been resected. And a lot of people are trying to use Raman microscopy along with autofluorescence and diffuse reflectance and what have you in order to look at that tumor sample. There's a lot of other applications that have come up as variants or simpler variants of spontaneous Raman. For example, spatially offset Raman spectroscopy has made a big impact in looking at and probing bones, right? So if you actually separate your excitation and collection optics or the probes, you can actually probe deeper. So deeper imaging is something that is becoming very much in the vogue, if you will, very much of interest, of significant interest in the Raman community. Then, of course, with all these variants, if you look at cars, for instance, you get these beautiful lipid signatures, which stimulated Raman. A lot of people are looking at different kinds of lipid signatures, but also a number of our collaborators are looking at cutaneous lesions, at melanomas, for instance, right? So in the dermatology clinic, there's a number of applications. Then you come to surface enhanced Raman, things that I was presenting, and there is huge possibilities, tremendous really, in liquid biopsy, right? So where you are actually withdrawing blood, but very small amounts of blood, and you're trying to study if there are tumor-based biomarkers that are circulating in the blood samples, right? Or that are circulating in systemic blood, and you can actually take that out and see. So very similar to, for instance, what you would do with diabetes, right? So you would actually measure blood glucose, but here you're measuring tumor-based biomarkers that are circulating in the person's blood sample. So a number of interesting applications. Now the challenges, just one quick word on that. Well, I mean, there's clearly no Raman-based product yet, right? So there are certainly challenges. I will say this, I think some of it has to do with a general disconnect between the Raman community or the search community, or more generally in the optical spectroscopy community and clinicians. As people learn to speak each other's languages, there is greater adoption of Raman. And I think over the next 5 years, you'll see a lot of that being pushed through the clinical pipeline.
Okay, thank you.
Thank you very much, Professor Barman. It was a very informative talk. Thank you very much.
Thank you. Appreciate it.
Next talk in the line we have by Professor Steve Stegan.
It's me.
So Professor Steve Stegan is an associate professor of mechanical engineering and founding coordinator of manufacturing engineering program at University of North Florida. Dr. Steve completed his PhD at the University of Connecticut in mechanical engineering 2013 and joined UNF in 2014. Steve has taught industry-sponsored senior capstone design for 5 years and also teaches in the area of control automation and material processing. Research has focused on surface and interface engineering with the sponsored project totaling of more than 500K US dollar from NASA, Johnson & Johnson 3D printings, and many other funding sources. Recent work has focused in the area of applying metallic nanostructures fabrication by using GLAD and other physical vapor deposition method as substrate for SaaS application. Steve is also a serial entrepreneur, having launched 4 startups. Most recently, founded Mesoglue, a company focused on the development of a low temperature materials for joining and thermal management. So he's talking, is going to talk about the detection of SARS-CoV-2 spike S1 glycol protein using GLAD nano rods in SARS and neutral network. So over to you, Professor Steve Stegan.
Great, thank you. So I will bring this up, and I will bring this up here. Can everyone see my screen?
Yeah.
Outstanding. So I'd like to thank you all for coming and listening to the talk. I saw that it was the last talk in the schedule, so thank you for sticking with it and, and joining in on this talk. I'd like to say also that I'm very happy to be talking to you all. I've worked a lot with this group, the folks and the organizers and everything, and it's great to see faces and put them along with names, right? So we always work on reviewing each other's papers and seeing the latest work as it comes out on Google Scholar. So it's great to see everybody and to listen to some of their latest work. So first, what I wanted to do is I just wanted to talk a little bit about University of North Florida and what we do here. We're a lot of people may think of Florida and think of University of Florida. So we're actually in the northern part of Florida, very close to southern Georgia. We're an up-and-coming research school here. So when I started here 8 years ago, we were a regional comprehensive school, meaning we did not have a PhD program in anything, and we were working on building our program out. Thanks to money from the state of Florida, we were actually able to go ahead and build a really world-class microscopy facility. So this is the material science and engineering research facility that we have here now. And we've actually partnered up with TestScan to get some of their latest and greatest equipment. We've also partnered up with Oxford and Shimadzu. So some of the highlights are that we have some of the best Oxford EBSD equipment, and we have the highest resolution SEM put in the state of Florida. So that's our bragging right there. And this all really came up from the ground. 5 years ago, we didn't have a single analytical instrument here. So we've been working really hard on building that. In my lab here, I actually came from the lab of Han-Shen Huang, who's now dean at University of North Texas, and he did a lot of atomistic simulation. And before that, he was at RPI, then University of Connecticut, Northeastern University. Now he's at UNT, so some of you probably know him. But what we do is we have physical vapor deposition facilities. We have a small chamber. We have various other things. We have capabilities of sputtering, thermal evaporation, E-beam. And this is just some of the work that we do, kind of highlighting this. My group is generally between 5 and 7 people in terms of all MS students right now, and we have mechanical engineering as well as material science and engineering students. So we're staying very busy, and we hope to, within the next 2 to 3 years, expand to a PhD program. Also, I have the goal of bringing on a postdoc, pretty much steady state postdoc, so we're pushing for more funding in that area. So hopefully maybe one of the students from your group, one of your graduates, can come and join as a postdoc. So here's the overall big picture of what we were trying to do. So if you think about the background, I'm a mechanical engineer. So unlike material science and unlike basic physics, we really try to make devices and system level things and try to do our development part to push these device and system level things. And we were approached, so this was at the very beginning of the pandemic, we were approached by the Jacksonville Energy Authority, who's actually a group that goes and monitors wastewater as well as the electrical energy. And one of the things that they were trying to do is they were trying to use the rapid PCR test to be able to detect predictively if there was SARS-CoV-2 in the wastewater. And one of the interesting things that was found through research at the University of Arizona, and why they were motivated to do this, was that you could detect rising levels of the virus in the wastewater 4 days before you were able to detect it within the population. So we thought this was something very important to do. And together with the team, we started working on an auto sampling setup where the auto sampler would be installed at various key facilities throughout the city. From the auto sampler, then it would take, and we're attempting to put a remote Raman setup in with this, as well as some auto-fed nanorod substrates. And the goal is actually to send the data out remotely through the web, upload it to the cloud, and then use that along with artificial intelligence and neural networks to try to back solve and predict where the hotspots are inside the city. So to give you context, Jacksonville is a major metropolitan area. It's probably not one that you've heard of if you're from outside the United States. You might think of New York or Boston, Chicago, Miami, but Jacksonville is over 1 million people, and it has a very dense urban core. So it's a relatively large city, and this kind of detection is really key. So what my lab has kind of been doing is twofold. So we looked first at the hang on one second. We looked first at the overall structure, right? So we looked at the silver nanorods and various other things, and we were trying to see, can we just do this detection with the Raman spectrometer? The next thing is, how can we bring this to a system level, right? So that's the things that we needed to do. It looks like my camera has frozen. Can you all see me or hear me?
No,
can see.
no, I
Okay,
can't.
excellent. Outstanding. Thank you. So our approach to this was a very classical approach, right? So JP, I'm sure that you guys have done a ton of work and stuff very similar to this. I know Yiping has done a ton of work and stuff similar. I love seeing the work come out. I love seeing the postdocs and the PhD students come through and do this stuff. So what we thought in our minds was, how can we preferentially attach the SARS virus to the surface of silver nanorods, so we can get it in a good proximity, so that we can get some detection of trace amounts. And the thing that we looked for here, we had to go to biology and work with some biologists, and what we discovered was that if you take the spike S1 glycoprotein on the exterior of the shell of the virus, you can actually attach it to, and it preferentially binds in the body, to this ACE2 enzyme. So the ACE2 enzyme is critically important. It's all throughout our body. It's in our mucous membranes and everything, and this is one of the major pathways for the virus. So what our attempt to do was, or what our goal here was to take the ACE2 and to attach onto the ACE2 the spike S1 glycoprotein preferentially. Okay, so you say you cannot see me, so let me check here. The camera is saying that it's live.
Yeah, it is actually saying some problem due to the low bandwidth or some local computer condition. So please go ahead. Yeah, please go ahead.
I'll continue on presenting.
Yeah.
And I've just actually frozen WebEx now while trying to go into the camera. So I'll continue presenting, just talking.
Sure. Please go ahead.
So again, kind of talking through this. So what we did was we sourced out ACE2 enzyme, which we were able to get from Sigma Aldrich. We were also able to get the spike S1 and S2 glycoproteins. And we ran into some really interesting issues.
Professor Stegan, is your screen frozen at your end?
Hi, you're not audible.
Hello, Professor Stegan.
I think there is something wrong with him, with his network or.
Yeah, it was showing actually some network issue.
Yes.
He will wait.
Yes, I think he will join soon.
Yeah. Hello, Professor Stagan. Can you hear me? Yes, I think he will rejoin and then things will be okay.
Yes, he will rejoin.
Yeah, let us wait.
Yeah. We will wait some time and see if Professor Stegan can rejoin. because of some technical issue, we could not hear Professor Stegan. Professor JP Singh, you want to say something?
Yeah, I think we tried to contact Professor Stephen Stegen, and I think there is some technical maybe network issue. So, but really the topic was very interesting and very relevant to the current time. So what we can do, maybe we can ask him to maybe send us the recorded lecture, and it can actually go along with all the recorded lecture which we are going to have is this meeting, and then we will make it available to all the participants separately, so participant can actually see that lecture, see his lecture actually, and get benefit out of it. Okay, so now this I think maybe Mukesh, you want to say something, or otherwise I will have to
No, actually, I attended the conference e-mode, but I'd love to be like present that in person, and I attended that last time and really enjoyed. And Professor Burman rightly said that like once somebody was asking the question, that really needs some long discussion, and that is only possible when we have extra time during the tea or during the food or during extra hours. So that actually I personally missing that. So hopefully everything will be like okay sometime in like future, maybe this year end, and then we can probably meet again with all of the like eminent speakers in Delhi sometime. So with that, I would like to thanks all the speakers in this session, and thank you very much, and over to you.
Yes, so finally the
Professor Mukesh Kumar.
Yeah.
For chairing this session. So now I would like to request Professor JP Singh, the convener of the conference, for the closing note remark, or please say a few words. Over to you, sir.
Okay, so it has been our pleasure to host GLAD 2021 at IIT Delhi, and we have listened excellent talks by eminent invited speakers. And this meeting was really global in the sense that we have speakers from all over the world showing their exciting results. It is good to see how this field of GLAD is growing, and I'm sure that participants must have benefited by attending this conference. I thank all the participants for attending this conference, and I thank all my group members, especially Conference Secretary Jyoti, and for technical support Shashank, for giving the technical support for this difficult time, and we didn't get any support from basically our IT team also. So I also thank all the chairpersons for their help in conference organization. And I hope to see you in the next GLAD meeting in 2023. Now, I saw Professor Iping attending all the sessions practically without getting any sleep. So now I request the co-convener of this meeting, Professor Iping Zhao, to make the comments or final and announcements. Professor Zhao.
Thank you, Professor Singh. And I would like to thank all the speakers to give wonderful talks on various aspects of GLAD. I noticed that there are two significant features in this conference. First, the speakers are truly from all over the world. So we can see how the GLAD actually spreading around. Second, there are so many emerging areas in GLAD community, including active matters, plasmonics, sensors, device, renewable energy, biomedical application, etc. And new growth strategies and also fundamental understanding of the growth mechanisms has been also proposed. All those shows that the GLAD community is still a very strong and also fruitful field. I'm expecting that in the near future, more unknown and innovative developments and also applications will be explored, and many fundamental scientific questions will be answered based on glancing angle deposition. So there are a total of 95 participants from all over the world to attend this conference. I would also like to thank all of you, especially those in North America who has to stay over the light. It is always my pleasure to see more and more people entering the GLAD field, bringing innovative and fresh ideas and moving the field to new and exciting directions. I hope more and more research groups will join our community and use the GLAD in their research. I would like to sincerely thank Professor J.P. Singh, Ms. Jyoti, the section chairs, other conference organizers, and also the students in IIT Delhi to make such a successful and a wonderful meeting in such a very difficult time in India. The GLAD conference has been organized by Professor J.P. Singh and also IIT Delhi for twice. One is in 2018, and this is the second time. I believe that everybody over here would like to continue this conference in the future. Fortunately, Professor Cai-Ching Han from Jiangsu Normal University in China is interested in organizing the next GLAD conference in 2023 in China. And if any other people who are interested in organizing future conferences, it's always welcome to discuss with Professor Singh and me. Finally, I hope everyone will stay safe and healthy, and I will see you all in 2023. Thank you very much.
Thank you to the organizers.
Thank you, everybody.
Yeah, thank you, everyone. Okay. So
I'll see you guys in the future.
See you guys in future. And next meeting maybe.
Okay, thank you everyone for your kind attention and participation. Thank you all.
Yeah. Thank you
Bye.
all. Thank you. Bye.
And goodbye. Stay safe.
See you. Thank you.
See you
Bye-bye.
next time.
Okay.